Okay, so we're almost done here with the vector calculus notes, notes 3. Just a few more slides left. So I think the plan for tonight is to do that first. Finish talking about the curl, a couple other little things. And then the main topic of this afternoon is going to be Maxwell's equations, notes 4. Okay, probably we won't get any further than that, but if we do, next on the agenda is going to be notes 5, which is the Poynting vector and Poynting's theorem, which is talking about the flow of power in an electromagnetic field. Okay. All right. We started talking about curl last time. First of all, let me point out that, in rectangular coordinates, we write curl as del cross A. If you remember what the del operator is, it's literally del operator cross the vector function, and that gives us this mathematical form right here. It's a little more complicated to derive in cylindrical or spherical, but it is in the back of the Kate and Buck book. And if you want to see that, please read it. But here's the curl in cylindrical or spherical. Okay. But we were talking about the physical interpretation. And let me go back to that and review just really quickly again. So now remember that the curl of a vector function is another vector function. So if you give me some vector function A and you say the curl at some point, like where this red dot is, that's going to be a vector there, a vector. And like any other vector, it's going to have 3 components. In rectangular, that would be X component, Y component, Z component. So we can talk about what the X, Y, Z components of curl are. And here's the reminder of like how we interpret the X component of the curl at this point right here. Point your thumb in that direction, X direction. Make a little path that goes around your thumb. Usually people use rectangular, but doesn't have to be. Okay, a little area here. And then you integrate the vector function going like in that direction, counterclockwise around the path, and then divide by the area of the path. Take the limit as the area shrinks down. And that's what's called the curl, the X component of the curl at that point. Okay. And similarly for Y and Z components, as this slide shows here, this exploded view. Taking the curl at some point, the origin, you've got the path CX, CY, CZ, all defined with the right-hand rule, fingers of the right hand giving you the sense of integration. Okay. Now, we talked about how you can interpret physically the component XYZ of curl by introducing something called the curl meter. And I sort of brought one with me here. So, sample curl meter, if you don't want to see one in real life. It can also be used to stir paint, but I'll call it a curl meter, okay? So it's basically a little axis there and a bunch of vanes, right? So if that's the X direction, and I want to measure the curl in the X direction, I point the axis in the X direction, and I look at how much torque there is. Okay, now remember, torque has a right-hand rule too. So put the thumb in the direction of the axis. Here's the fingers of my right hand, right? So if it wants to spin in that direction, there's a positive component of curl in the X direction. If it wants to spin the opposite way, there's a negative component of curl in the X direction. If it doesn't want to spin at all when I point it in the X direction, there's no X component of curl, right? And similarly for Y or Z. Okay, so that's how we can think of measuring X, Y, Z component of curl. Okay, now that's how you think of it if the A vector is like velocity of water. If it's something like the electric field, we can't really visualize it, but it's the same kind of principle. Okay. Now let's go and do this example here. Going back to water, you can see we have like a riverbed here. And let's take the velocity of the water to be this made-up function. It's flowing in the X direction. See the red arrows are the velocity of the water. So the water is flowing in the X direction. And what's the X component, which is really the velocity of the water? It's taken to be the function Y. Now, Y is running up from the riverbed, the bottom of the river. And you see how the length of the arrows increases. So the water velocity is increasing as you go up in this fictitious river. It may be semi-practical because in a practical river, probably water is flowing slowest at the bottom because of friction and probably fastest at the top. Probably not linearly, but anyway, just a made-up example, okay? So anyway, with that assumed function for the water velocity, let's calculate the curl of the velocity function and see if it matches with what we learned about this paddle wheel here, okay? All right, so if this is the given function, what are the components? X component of velocity is, of course, everything in front of X hat, so it's just the function Y, right? There is no y hat or z hat here, so there's no y or z component of velocity. Now, velocity is given in rectangular coordinates, so of course it makes sense to use the rectangular form for curl, right? And there's that formula one more time. Okay, now with the green strikeout lines, I just removed everything that's a Vy or Vz, because there is no Vy or Vz in this function here, right? There's only a Vx. Now, Vx appears two places, here and here. Now, here it says partial of Vx with respect to z. Remember, here's the Vx function, just y. Of course, the partial of y with respect to z is 0, right? Of course. So that's gone for a different reason. So there's only one component that survives, minus z hat partial of Vx with respect to y. So you just end up taking partial of y with respect to y, which is, of course, just 1, right? So with the minus sign here, here's the final answer for curl at any point in the river. Okay. Now, usually curl of a vector function is another vector function that changes with position. But in this particular example, because it's so simple, notice the curl is not really a function of position. It's constant everywhere in the river. That's just, because this made up function is so simple. Okay. But in this case, it's got a constant curl. It's pointing in the z hat direction, and the component v sub z of the curl, the z component of the curl is -1. All right, so -1 is the z component of the curl. And the interesting thing is just the fact that it's negative. Now, let's take that curl meter that I just showed you and put it in the river and point the axis in the z direction, which is coming out of the screen towards you. Okay, see that? And now, which way is it going to spin? The z component of the curl is negative. Put your thumb, just visualize this, put your thumb of the right hand pointing out of the screen in the z direction and look at the fingers of your right hand. Do you agree that the fingers of your right hand are going around like this counterclockwise? Do you agree?
Yeah.
Okay, now the z component of the curl is negative though, right? So that means this paddle wheel, this curl meter, wants to spin going clockwise, right? Opposite to the fingers of the right hand. Does that make sense? Now, that's what the math tells us. But let's just see if it makes physical sense. Okay, now just visualize in your mind this water rushing past the paddle wheel. And remember, it's getting stronger as you go up. Okay, remember that. So look at the water as it hits the vanes of the paddle wheel, putting a force on them, and therefore giving the torque on the paddle wheel, right? So notice that the water has a higher velocity here than, let's say, down here. So when the water hits this vane, it's going to have more force than this one, right? So which way does it want to spin? Clockwise, of course, right? Agrees perfectly, right? Now, according to the math, the curl only had a z component, not an x component or a y component. So now we have to do another visualization. I don't have another slide, but just visualize it. Take the paddle wheel now and point the axis of the paddle wheel so it's in the x direction. Okay, well, so in other words, if this is the x direction, I'm doing this. And remember, the water is also flowing in the x direction, right? Paddle wheel want to turn? No, because the water is just sliding parallel to the vanes, right? Makes perfect physical sense. It agrees with the math. The math says there's no z component of the curl. Water is rushing by in the x direction like this. How come it doesn't want to turn now? Right, equal force. So no net torque, right? It agrees with the math perfectly. Yeah, please, do you have a question? So like this. So the water's going the x direction. If I'm pointing the axis in the x direction, there's no force whatsoever on the vanes, right? Right, because it's going parallel, it does not impart force to the vanes, right? You agree? It just slides past it, right? Right. The only part that exerts a force on a vane is part of the water that hits perpendicular, right? Yeah, so like that, there's no force, therefore no torque. Like this again, there will be force on this one. There will be force on this one as the water hits like this, but equal force, right? So no torque, no torque. Okay, the water might want to push the whole paddle wheel, right? But I don't care about that. There's no torque, right? And that's what's relevant to the curl. Make sense? Okay, everybody? Okay, good. All right. So I hope that kind of reinforces your understanding of curl that you learned back in calculus. Okay, let me point out that there's determinate forms for the curl in all three coordinate systems. Now, this is the one where I talked about last time, the good old determinate way of taking the cross product in rectangular coordinates, right? You got a cross product of two vectors, something cross something. Remember, the del operator is just treated like any other vector. So x component, y component, z component, right? So if you expand this out, of course, obviously you just get this one right here, right? Now, what's not so obvious is that if you look at the cylindrical and spherical forms of the curl, they can also be written in the determinate form as shown here, but it's pretty messy, really almost too messy to memorize. So I'm not sure what the advantage is. Probably you might as well just stick with these, right? But in case you're curious, yes, in cylindrical and spherical, you can also have determinate forms, okay? All right, and lastly, let me just review a couple of important theorems. I'm not going to give proof, but you can read that in the book. Two important theorems, the divergence theorem and the Stokes' theorem. So here's the divergence theorem. And then these theorems are useful for deriving other things, as we'll see probably today and next time. So divergence theorem applies to a volume, three-dimensional volumetric region of space. And of course, any three-dimensional region of space is bounded by what we call a closed surface, right? No holes in it, closed surface. And as usual, the symbol n hat means normal or a vector perpendicular to the surface. N hat means unit normal. So a unit vector, length one, unit vector perpendicular to the surface. Now, there's always two choices of a normal, one that points out and one that points in. The normal convention in almost all these theorems is outward normal. So n hat is understood to be the outward pointing normal, okay? Then the divergence theorem says, if you integrate throughout the three-dimensional volume of divergence of anything, any function, it's equal to integrating over the surface, and it's really a closed surface, right? Closed surface integral of the vector dot the outward normal. Okay, so that is the divergence theorem, applies to any shaped volume bounded by any surface S. The other one that's very important is Stokes' theorem, which is named after a mathematician, George Stokes. And it applies to a surface S that is not closed. This is a closed surface, right? This is what we call an open surface. Visualize it, if you will, as an upside down bowl, like a soup bowl or a cereal bowl turned upside down. All right. So this is the bowl. It's called an open surface. It's got this open face. In other words, if I'm coming along here, I can go inside the bowl, right? That's what we mean by an open surface. Now, if you think about it for a second, here's again the normal. Now, if you think about it for just a second, maybe you'll agree with this, that if you take any kind of a bowl shape or an open surface, it's got to end on something that we can call a closed contour C. The rim of the bowl is a contour, but it forms a closed path. Go back to where you start, right? Closed path. So Stokes' theorem applies to an open bowl-shaped surface that's always bounded by a closed contour or path C. Okay? Now, the bowl is arbitrary in shape, right? And also the C is kind of arbitrary as long as it's a closed path. One special case is if the path C is flat. And then not only is the path C flat, but then you squash the surface S down to become flat too. So a flat surface bounded by a flat contour. That's a special case, but Stokes' theorem applies in general to any kind of crazy bowl that's ending on a path C. Anyway, now here's the Stokes' theorem. Integral over the bowl of the curl of any vector function dot n is equal to the clothesline integral, because it's a closed path, of the vector function dot dr, the line integral of a dot dr. Now, there's a note here about the direction of the unit normal, okay? You can say there's a right-hand rule, meaning that if your fingers of the right hand go in the direction of the path C, here I've chosen counterclockwise, but anyway, if your fingers go in the direction of C, then look at the direction of your thumb. Now your thumb, now the unit normal is changing direction. You go all over the bowl, right? But still, the thumb of your right hand is going to have an overall sense of either up or down, right? If it's the right hand, it's going to up, left hand down, right? So you can see if the path is going like this, counterclockwise, that the thumb of the right hand is going up. So what does that mean? In Stokes' theorem, N is the unit normal that has the net upward direction. Yeah, it's not always pointing vertical, but no, it's a net upward direction. Okay, so that's getting the unit normal right in Stokes' theorem. So another way of saying it is if C always goes counterclockwise, the unit normal is always the outward normal to the bowler. Okay, does that make sense? So that's Stokes' theorem. Okay, and again, if this was a flat contour and I squashed S down to a flat surface, then N would be a fixed direction unit normal, always pointing just straight up in what we call the Z direction, right? Okay, all right. Okay, there's your review of vector calculus. I hope you enjoyed it. All right. If you want more, let me remind you one more time that, of course, you can see it in the books, of course, but let me remind you that the 3318 notes do a lot of in-depth discussion about vector calculus. And I'm kind of partial to that. That's one of my favorite classes, so I'll invite you to read those notes if you want to see more details about the vector calculus. Okay. All right, but that's enough for us here. All right, so let's fire up notes 4 here, Maxwell's equations. I hope you all have your Maxwell coffee cup. You do, don't you? No? Oh, that's a shame. Okay. Okay. Now, again, there's that same engineering course web server website, 3318. And here's some selected notes that talk in a lot more detail about each one of the 4 Maxwell equations. Okay, so I'll go over it kind of quickly, what they mean and everything. But if you want to see a lot more detail, probably even more details in the books, look at the 3318 notes, okay? Okay, first of all, notation. In Maxwell's equations, we see 4 electric fields, well, 4 fields, sorry. And here's what they are, and here's what the official units are. Okay, so E is called the electric field or electric field strength. Now remember that if it's in the time domain, these are all that hand script SF5, remember? Okay, if I go to phasor domain, then of course that's going to be the regular times Roman 5. D is the electric flux density, coulombs per square meter. It goes hand in hand with E, as we'll see in a minute. Okay, sometimes people might get sloppy and call them both electric fields, but really this is electric field and this is electric flux density. And similarly, there's 2 sort of magnetic fields. Again, people might sometimes just call them both magnetic fields, but really H is the official magnetic field or magnetic field strength. Okay, just call it magnetic field. And B is the magnetic flux density. Okay, Webers per square meter. And by definition, a Tesla is 1 Weber per square meter, named after the famous person, Nikola Tesla. Okay, same as probably the car is named after, right? Okay, and all the units there. Okay. Now, also, as we'll see in a second, in Maxwell's equations, we have the electric current density appearing, units of amps per square meter, and I'll review what that means in a second. And then rho V, the volume electric charge density. Okay. The symbol rho is used in various ways. Sometimes, in cylindrical coordinates, rho means distance from the z-axis, for example. Sometimes in mechanics, I think rho is used for density. But anyway, one of the meanings is electric charge density. The V indicates volume because there's different types of charge density. And you can talk about that more in 3318. But rho V means the volume charge density, coulombs per cubic meter. So if you have like a cloud of electrons floating in space, that would be a volume charge density, or a cloud of protons floating in space. Okay. You can also have charge on a surface, which is called surface charge density, or charge along a line, which is called line charge density. Or, of course, you can have 0 dimension, which is a point charge, right? So different dimensionalities, but this is a 3-dimensional volume charge density. Okay. All righty. So this slide is simply giving, in the MKS system, what the standard units are for length, mass, and time, but you already know that, I think. And let's see, and here's just, in the MKS system, all the different prefixes that go along with different units, kilo, milli, et cetera, but you probably have seen all that before. And see, let me do one quick thing though. Let me just stop for 1 second because I noticed this may not be the latest version. Let me just see if I have a little bit later version on my flash drive. It's no big deal, but in the later version, I think I corrected a couple typos. Let me just see if I can go to the later version here. Yeah, okay, there we go. Okay. Okay, so here they are, along with a picture of Maxwell. There they are, the 4 Maxwell's equations. And of course, what do you see in them? Obviously, you see divergence and curl, right? So that's why it's so important to really have at least a basic understanding of what divergence and curl mean. Okay. Now here's some from Wikipedia. Here's some interesting sort of history about Maxwell. By the way, let me point out one thing here. His middle name is spelled with an E, but it's pronounced Clark, as if it was an A. Okay, so his name is pronounced James Clerk Maxwell, a Scottish mathematician and theoretical physicist who did many things besides actually Maxwell's equations, if you read all this off here. But anyway, probably his most famous contribution is Maxwell's equations. Okay. Now, Maxwell himself did not postulate equations that look like this. He formulated a fairly messy system of equations. It was actually 20 equations, 20 variables in it. So it's very difficult to interpret and understand. Then another very famous person came along and gave us the modern form of Maxwell's equations. Any guess who that might have been? Oliver Heaviside, the famous physicist and electrical engineer. Right, very good. In fact, that's why some people even call them the Maxwell-Heaviside equations, right? Now, in fact, Heaviside, of course, he did a lot of wonderful things, right? The unit step function, the delta function, operational calculus. But one of the things he did is he basically invented what today we call vector calculus or vector analysis. And then once he did that, see, Maxwell didn't have the del operator and divergence of curl. But then Heaviside introduced that and then recognized that Maxwell's equations could be put into this nice form here. Right, so it was really a tremendous leap forward. Okay, but there is the 4 Maxwell's equations, and with their names, Faraday's law, Ampere's law, magnetic Gauss law, and the electric Gauss law. Okay, now I'd like to walk you through these questions. They're kind of interesting. Let's see if this makes sense here. So, question: when does a magnetic field produce an electric field? And I'll give you a hint. To help us answer that question, I propose looking at the first one called Faraday's law. Question again: when does a magnetic field produce an electric field? Any guesses? A little louder? Right. So notice if you have an electric field here being produced by a magnetic field, then you're only going to get something, of course, the right-hand side is not 0. And that means B has to be changing with time, right? If I just have a magnetic field that doesn't change with time, let's just say, as an example, I have a magnetic field coming out of a bar magnet. Okay, it may be a very strong magnetic field, but it's not changing with time, right? So the right-hand side is going to be 0. It doesn't produce any electric field. I can have as strong a bar magnet as you want, or even an electromagnet with a DC current, but it's not going to produce an electric field. It only produces a magnetic field, right? Okay, but a magnetic field changes with time, that produces an electric field. That's what Faraday discovered. And that's what's called Faraday's law. Now, this next question is very similar. When does an electric field produce a magnetic field? Now, I'll give you a hint. Let's look at this one, Ampere's law. Now, ignore the current density just for a second. If we were in free space, for example, it's not going to be current. So just ignore that. So just look at this equal to this. So same kind of question. So when will an electric field, it's really called the flux density, but I'll just call it electric field right now. So when will that produce a magnetic field? Exactly the same thing. Okay. Third question. When does a current flow, this is what's called the current density vector. So this represents current flow. When does a current flow produce a magnetic field? So look at this equation again. When does a current produce a magnetic field? Does it from Ampere's law, does it appear that we need to have a current changing with time to produce a magnetic field?
No.
No, you're right. So even at any current, even a DC current can produce a magnetic field. And indeed, if you have a wire connected to a battery carrying a DC current, it's going to produce a magnetic field. Okay? So any current produces a magnetic field. All right? So there's two ways to produce a magnetic field. Current, whether it's changing or not, or a changing electric field, right? Okay? That makes sense? Okay. Now, if you look at these guys here, and we do a lot with these in 3318, the electric Gauss law says divergence in electric flux density vector is rho v. Remember, that's the charge, the volume charge density, and there's no time derivative there either, right? So what that equation says is charge by itself can also produce an electric field, right? So the ways you can produce an electric field are with charge, whether it's changing or not, or a changing magnetic field. Either one will produce an electric field. Does that make sense? Okay. Okay. Now, the fact that changing magnetic field produces an electric field and changing electric field produces a magnetic field is kind of very fortunate. Either one changing produces the other one. So that means, as we'll study later in the semester, we can have these things called electromagnetic waves, like a plane wave propagating through space. A wave comes from a satellite and goes through space, travels just fine, even though it's in vacuum, right? It's not like an acoustic wave or a wave on the ocean that requires a medium, right? Okay, a long time ago, people talked about the ether. They thought that EM waves required some mysterious ether to propagate. No, it goes perfectly fine through vacuum. The way it works is the electromagnetic wave has both electric and magnetic fields, both simultaneously, usually perpendicular, as we'll see later. But anyway, as each one changes with time, it causes the other one to exist. So each one causes the other one. It's a perfect kind of synergy there. It doesn't need anything else. Doesn't need any medium or anything like else. So it's really neat. Okay. Okay. Let me also wait. Let me just pause just 1 second here. I'll come back in just a second. Let me go back to this other document here. I just put this on the Blackboard this morning, but it's kind of neat. You might want to read it just for fun. It's taken from a magazine called the Microwave Journal, and it's called In Search of Maxwell. Okay. The author is actually a friend of mine, James Ratio. There's a picture of him. Okay. And he's actually the head of a company called Sonnet Software. That's one of the leading industry softwares for EM software, the EM analysis type of software. But anyway, he's a big fan of Maxwell and he's a history buff. So one of the things he did is he actually took his own private journey back to Scotland in search of where Maxwell was born and raised and all the historical facts about Maxwell. And he published in this magazine kind of a sort of a diary of his journey there to Scotland in search of all the facts about Maxwell. It's pretty short, as you can see, it's just a few pages, but it's really kind of nice reading if you want to read it. So I invite you to read that. Okay. Okay. Anyway, back to where we were. Okay. Now, because current density and charge both appear in Maxwell's equations, I think it's probably worthwhile to review exactly what they mean. Okay. So rho v is the volume charge density. And remember, it appears right here in the electric Gauss law. So what does that mean? Okay. Visualize a cloud of charge, like, for example, a cloud of protons floating around in space. Okay. Protons are, of course, positive charge, electrons are negative charge. So if it's protons floating around space, the rho v would be positive, right? Positive function. Now, just imagine a little sort of sampling cube. Okay, it doesn't have to be cube shape, but a little sampling cube, let's say. And it's got some little volume, dV, centered at the sampling point XYZ, and it scoops out a little bit of charge. Now, if you magnify what the cloud looks like, you're going to see protons, right? And now the cloud doesn't have to be uniform. So see how it's shaded darker as you go from left to right? So that could be the protons getting closer together as you go from left to right. So the charge density is getting higher as you go from left to right. But anyway, if I want to know what it is at this red dot here, the sample point, here's the definition. Just take the amount of charge in the cube divided by the volume of the cube, let the volume get smaller and smaller until it really becomes differentials, and that's the volume charge density at that point. So it's exactly analogous to how in mechanics you define mass density, right? Except we're using charge here instead of mass, but same kind of principle. Okay. So hopefully that's a common sense definition of what volume charge density is. And again, you can have charge on a surface, charge on a line, but in Maxwell's equations, it's volume, charge, density that appears. Then let's review the current density vector, because that appears in Ampere's law again. So what the heck does that mean? Okay, and the units are amps per square meter. Okay, now current, this goes back to basic circuit theory. Current is the flow of charge, right? We all know that. Okay, now, yeah, please go ahead. This one here? So you mean here? Yeah, so the symbol for the current density vector is a J. It's supposed to be a J, right? Okay, but this is what J looks, uppercase J looks like with a hand script SF font. Yeah, so remember, it's hand script SF font, so things look like this, right? And hand script SF font is used to denote, arbitrary time varying functions. When I'm in the phasor domain, I'm going to use just a regular times Roman, okay? Okay, so J is the current density vector, and current is the flow of charge. So let's assume I have positive charge in some hypothetical medium moving from left to right. Now, in modern times, the standard IEEE convention, although it goes back to Benjamin Franklin, you call it the Benjamin Franklin convention if you want. But anyway, the IEEE convention is that current is defined to be in the direction that positive charges move in. Now you can just call this the X direction if you want. I didn't label it. You can call it X if you want. So if I have positive protons moving in the X direction, I'm going to say that we have a positive current flow in the X direction. That's our standard IEEE convention. Now, in a real medium, like a copper wire or an aluminum wire, nowadays we know that it's really electrons that are moving. Benjamin Franklin didn't know that, but now we know it, right? Okay, this convention still sticks. But no problem, as it says here, if negative charges are moving, we just pretend that positive charges are moving in the opposite direction. So if I have electrons moving to the left, I can just say mentally it's equivalent to positive charges moving to the right. And so I've got a J vector flowing to the right. That makes sense? Okay. Now, usually, well, as I'll mention in a second, Ohm's law, but Ohm's law says that usually the J vector is going to be in the same direction as the E vector. In fact, Ohm's law actually says that proportional. J is something called the conductivity times the E vector. So normally they're in the same direction. There could be a battery, I'm not showing it here, but maybe a battery with anode over here and cathode over here. So it sets up an electric field in the X direction. So that's why there's a J vector in the X direction. Okay. Now, as the positive charge is moving, as they move and sweep past this reference plane, that means a current that's crossing that reference plane. We can call it delta I if you want. Crossing this little surface delta S, some little surface with some amount of square meters. Okay. Now, we define this, the J vector magnitude, to be the amps per square meter crossing this perpendicular surface. Okay, so we would say that amps, called delta I, crossing this little surface delta S, is going to be the magnitude of the J vector, which is amps per square meter, times the surface area in square meters. So, of course, that's going to come out to be amps, right? So J itself is amps per square meter. There's amps crossing the surface, and it's the number of amps per square meter crossing this perpendicular surface. That's the meaning of the J vector. Okay, the magnitude of the J vector. The direction, of course, is just whatever direction it's flowing in. This example is unit vector X, but it could be any direction. Okay, does that make sense? So that's the physical meaning of the J vector. Okay, current per square meter crossing a perpendicular surface. Okay. Again, for most normal materials, they obey Ohm's law, which is really an experimental law that J is parallel to E. E is what sets up the J vector, causes the electrons or whatever to start moving, hits them, gives a force on them, gets them moving, right? So anyway, every material has some conductivity. Taken from Wikipedia, here's some typical, fairly good conductors. You can see the conductivities. The higher the conductivity, the better the conductor. What's called perfect electric conductor, sometimes called PEC, perfect electric conductor, would be a hypothetical material with infinite conductivity, but it doesn't really exist in nature. Okay, a superconductor might come pretty close, but there's really no such thing in nature. But anyway, in our everyday world, silver is probably the best conductor we can find, but it's pretty expensive, right? So in real life, people are more likely to use copper or something like aluminum, but it's almost as good, right? It's still pretty high. Okay. And of course, a good resistor or a good insulator would be the opposite, right? A good insulator would be a material that has a very, very small sigma, right? Like a plastic or glass or ceramic or something. You make insulators out of them. Okay. What if I have current flow? Let's just keep it simple and say it's in the x direction, horizontal. Okay, it doesn't have to be, but let's just assume it. And then I have a tilted surface, a little delta S square meters, but it's tilted. Here's the unit normal, as we call it, to the tilted surface. Okay. Now remember, let me remind you, okay, that if I have a little surface perpendicular, we just say that the amps crossing it is the magnitude of the J vector, amps per square meter, times the square meter area. That's the definition of how we work with the J vector, right? If the surface is perpendicular. Current proton that is coming here and is crossing the surface, giving a current flow. But what do I do in this case if the surface is tilted with respect to the J vector? Now, here's probably the simplest way to think about it. You know, the protons are moving like this in the direction of the J vector. They've got a velocity vector. That's the same direction as the J vector. Now, any vector, as you know, can be broken up into different components. Now, of course, you can say X, Y, Z components if you want. But here's another way of thinking about it. Take the J vector and think of it as broken up into two components. So this blue vector is broken up into two components. One is going to be in the direction of the normal, okay? And one is going to be perpendicular to the normal, which is another way of saying parallel to the surface. See that? You can always do that, okay? Now, for the velocity vector that's parallel to the surface, you can interpret that as given the velocity component corresponding to protons that would just slide along the surface, right? If you just look at that velocity component, you know, protons sliding along the surface are not going to cross, right? So that component of the velocity vector or the J vector contributes nothing to the current crossing the surface, right? But the component of the velocity vector that's in the normal direction, that's the ones that are hitting the surface dead on and crossing the surface, right? So that's the component that contributes to amps crossing the surface. So in this general picture, here's what we do. We say the J vector dot the unit normal, take that component, which is really the component crossing the surface, and then time the square meter area of the surface. Now, there's really two directions to unit normal. If the picture looks like this, then delta I means the amps crossing this little surface going in the net left to right direction. If I would have picked unit normal going this way, it's the opposite, then this would represent the amps crossing in the net right to left direction. That makes sense? Okay, so that's how you get current crossing a surface, or at least a piece of surface, right? This could be one little piece of some larger surface here, delta S. Now, here's like a three-dimensional view of a complete surface, kind of like that bowl, for example, I was talking about in Stokes' theorem, something like this. Now, here's as crazy as you can possibly get. You got some kind of surface, doesn't have to be flat, some kind of a crazy shaped surface. At every point, there's a unit normal, and it can be changing directions everywhere on the surface. And in space, there's a J vector, and it could be changing, right? See, at different points on the surface, it's got a different direction, even got a different magnitude, right? Okay, so here's a little piece of the surface. So what do we do to do the complete surface? We integrate over the surface. Just imagine the surface broken above little pieces, adding all together, usual thing, calculus, Riemann sum, goes to integral, usual thing, right? So the total current crossing the surface, total amps crossing the surface is integral over the surface, J vector dot normal ds. Okay, and again, unit normal has two directions. If unit normal is out or upward like this, then I means the amps that has crossed this bowl going in the net upward sense. Does that make sense? Okay. All right. Now, that was a review of Maxwell's equations. Let's start doing some things with them. All right, first on the agenda is I'm going to derive what's called the law of conservation of charge, also sometimes called the continuity equation. Okay. All right. To derive this, by the way, the final interpretation of it, as we'll see, is that charge is never created or destroyed. Charge can only move from one point to another, which means current flow. After all the math, that's going to be the simple physical interpretation. Okay, but let's see if we can get there. Okay, we'll start with Ampere's law. Here it is. Okay. And I'll take the divergence of both sides. Now, in my review of vector calculus, I already said there's two fundamental identities that I like to call the zero identities. And you may have noticed you're being asked to prove them on the homework. Okay. Okay, but anyway, so one is One says divergence of any curl is 0. And the other one says curl of any gradient is 0, but we don't need that one right now. But divergence of any curl is 0. So that's neat. That's gone, right? So there's 0 there. Okay, and then of course divergence of these two guys. All right. Now, divergence of J, if I take this across the equal sign, divergence of J is minus the time derivative of divergence of D. Okay. Does anybody remember from what's called the electric Gauss law, one of Maxwell's equations, what divergence of D is? Right. So divergence of D was rho v, right? So divergence of J is minus the rate of change of rho v. And physically, this would say that, divergence is like a flow rate out of this little cube, if you remember, right? So it's like the flow rate of current out of a little cube is minus the rate of change of charge. Okay, but the nicest way to give a physical interpretation is to hold off until we get the final volumetric form of it. You can call this the differential or point form of the continuity equation, but usually physical laws are easy to interpret when they're in the three-dimensional or volume or integral form. So I want to go ahead and put this into the integral form. But there it is in what we'll call the point of differential form. Now, to head towards the integral form, which is easier to interpret, let's take any arbitrary volume you want. And let's go ahead, as it says here, integrate both sides over some arbitrary volume. In other words, just slap a volume integral onto both sides. Okay, so now I'm integrating over some arbitrary volume. Now, a few minutes ago, I just reviewed the divergence theorem, if you remember. And the divergence theorem relates to a volume integral of divergence of something. I called it A, arbitrary vector function. Okay, now it's J vector, but okay, whatever. But the divergence theorem says volume integral throughout a region of divergence of anything is integral over the closed surface S, right? That's something, the J here, dot the normal, the outward normal. Okay? That's the divergence theorem. Now, a second ago, okay, I just reviewed the meaning of this, right? Integral over surface J dot N is the current flowing through the surface, right? Okay, well, that's nice. So look what I have now. Integral over this closed surface, J dot outward normal over the closed surface, the complete surface. So if you believe what I just reviewed a second ago, the interpretation of this term is the total current, the total amps flowing out, because N is the outward normal, flowing out of the region V, in other words, crossing the surface S, flowing out. Okay. All right. So that's the physical interpretation of this. But anyway, so now this guy is equal to this from the divergence theorem, right? This guy is equal to this. So substitute in here, copy this down. So now we have this. Okay, continue on here. There it is. One more time. Now, to give a final physical interpretation, let me do one more thing, which I think is fairly practical. And what I'm going to do is I'm going to assume that, I guess, it doesn't have to be, but in real life, this is usually the case. I'm going to assume that the volume itself and the surface S are fixed and they're not changing with time. I mean, they could be, but usually they're not, right? In most practical cases. So let's assume that. So if that's true, that the volume and the surface S are stationary, then here, what calculus says is that it doesn't matter whether the time derivative is kept on the rho v or taken outside, because the volume itself doesn't change with time. That's what calculus tells us. So I can take the form that I have right now and just take the time derivative on the outside. Now, how does that help me? Well, remember, rho v is what we call the volume charge density. There's like protons, for example, floating around in here. It's the volume charge density, coulombs per cubic meter. If I integrate that coulombs per cubic meter throughout the whole volume, what am I going to get? The total charge, the total coulombs inside the volume, right? What I'll call Q enclosed, the charge enclosed inside the surface S, in other words, throughout the volume V. Q enclosed. Okay. All right. So the right-hand side is this minus the rate of change of the Q enclosed. And then remember, the left-hand side has a physical interpretation of the total current flowing out of the surface. Okay, let's call it I out. So the total current flowing out of the surface is minus the rate of change of the charge inside. Now, I like it better if I multiply both sides by a minus sign. And I'm going to say the negative of current flowing out is the current flowing in. I like that the best. And I get this equation here. So I'll leave that as the final answer. So the total current, here's like a J vector showing current flowing into the surface from the outside. Like you can visualize protons flowing in from the outside, okay? There's a current flowing in from the outside. The current flowing in, crossing the surface S, is equal to the rate of change of the charge inside. So what that means physically is if protons are moving, charge is moving, and they cross the surface corresponding to current flow crossing the surface, that current then causes a buildup of the charge inside. It's obvious because the protons, they cross the surface, they stay there, right? So because the current going in is equal to the rate of change of the charge enclosed, the charge has not magically disappeared, right? I mean, if you have current flowing in, protons crossing the surface, but there's no rate of change or buildup of charge inside, then what happened to those protons, right? They crossed the surface and they vanished, all right? Is that possible? Well, not if you believe that equation, right? If the current crosses, it causes buildup of charge. Those protons cross the surface, they stay there, they correspond to buildup of charge, right? So that's why it's called sometimes a conservation of charge equation, right? Protons and electrons, they never magically disappear, but they can cross the surface and then they cause a buildup of charge. Okay. Now, of course, if it's electrons crossing in, the rate of charge buildup will be negative because electrons have negative charge, right? But anyway, the current going in causes rate of change of charge buildup. Okay, there's the final conclusion. So does that conclusion make sense? Okay, it's kind of interesting. I mean, of course you would have guessed it. How can a proton or electron vanish, right? I mean, how can it be? But it's kind of interesting that we proved it from Maxwell's equations. It's kind of interesting, I think. Okay. All right, anyway, let's move on here. Let's see how we're doing on time here. Okay. So here they are one more time before Maxwell's equations. Okay. Now let me point out one thing here, which is kind of relevant for 3318, because again, in that course, it's kind of a statics course. Everything is statics, or low enough frequency, like 60 hertz for power engineers, so we can assume it's almost static. But anyway, look what happens if you're in statics, and I'll assume honest to goodness statics, which means no time variation at all. And you can have like a static point charge. You can have a DC current producing a magnetic field or a bar magnet, but nothing changing with time, complete statics. So that means all time derivatives are gone, right? So this term here is gone, right? This term here is gone. And following the 3318 notation, if I'm in complete statics, I'm going to go back to using Times Roman instead of hand script. Okay, just agree with 3318 notation. But anyway, but the important thing is this is gone and this is gone. So the four Maxwell's equations become like this. Okay, now notice though I've rearranged them slightly different than up here. Okay, so for example, I grouped these two together here and these two together here. Now it's interesting, look what happens in statics. We have two equations that both have electric field in them. Okay, really electric field and electric flux density, but again, I'll just call it electric field. Okay, we have two equations that have magnetic field in them. Okay, really magnetic field and magnetic flux density. Okay, but they're separate, independent pairs of equations. This pair has nothing to do with magnetic field. This pair has nothing to do with electric field, right? Okay, so that's a proof that in statics, Maxwell's equations decouple into two independent sets of equations, electrostatic equations, as we call them, and magnetostatic equations. Okay, in electrostatics, okay, you can see that what happens is that charge, look at this equation, charge produces an electric field. In magnetostatics, look at these equations, current produces a magnetic field, right? Okay, so in statics, electric field comes from one thing, and that's a charge. Magnetic field comes from one thing, and that's a current. There's no coupling between them like that. Okay, so and if you're like at 60 hertz, it's not real statics, but probably close enough. So power engineers often think this way. So if you have, let's say, a 60 hertz power line, an overhead power line, it's probably fair to say, to a very high degree of accuracy, that the electric field that I see standing underneath the power line is coming from whatever charge is on it. The magnetic field coming from the power line is due to whatever current's flowing through it. Okay, they're independent. Of course, and the electric field, which is related to the charge, also is related to the voltage of the power line, right? So electric field related to the voltage of the power line, magnetic field related to the current going through the power line. But those are two completely different things, right? Okay, all right. But of course, it's very different at high frequency, which is the opposite. High frequency, you have a microwave signal coming from a satellite, you have light coming from a light or something, and that's a wave going through space. Well, like I said a minute ago, the fact that things are changing with time is critical, because the magnetic field changing with time causes the electric field in the way. Electric field changing with time causes the magnetic field, right? So obviously you can't have a wave going through space coming from an antenna at zero frequency, of course, right? Radiation is a high frequency effect. Okay, and usually the higher the frequency, the more things tend to radiate. I mean, sometimes that's good. If you're an antenna engineer, that's good, of course. If you're a circuit board designer and you're worried about EMC and EMI, that's a very bad thing. You don't want this circuit board to radiate and couple something else, right? But anyway, higher frequencies tend to invite radiation. It's kind of a general principle. All right, so anyway, any questions on that? That makes sense? Okay. So we're doing time here. If I can just excuse me, just pause for 1 second here. I do want to start getting into the habit of taking attendance. Okay. Now, it's easy to convert all of Maxwell's equations into the phasor domain. Okay, remember, well, I'll go to this slide. Here they are in the time domain. Now, you know perfectly well from your circuits class, when you go to time domain and phasor domain, and we reviewed it here too, that time domain, time derivative goes to just j omega in the phasor domain, right? So in every here, j omega, here, j omega, in these two places, right? And then remember, I get rid of the hand script notation when I'm in the phasor domain. So here's Maxwell's equations in the regular phasor domain, right? Now, of course, in the phasor domain, these, remember, as I reviewed before, these are complex vectors, right? But they don't vary with time. The phasor does not vary with time, right? But so these are complex vectors, or phasor vectors, as we call them. All right. Okay, there they are. Now, next thing I want to talk about and review here is medium properties. So again, we have 4 quantities. 2 of them are sort of called electric field, and 2 of them are sort of called magnetic field, but they're strongly related to each other. And I want to review how that works. All right. Now, first, let's talk about the simplest case of free space. Free space means vacuum, although practically speaking, normal air is usually close enough to what we call free space. Okay, as opposed to being in a material like Teflon or something like that. But anyway, free space, then the electric flux density vector is related to the electric field vector by something that's defined to be epsilon 0, the Greek epsilon 0, called the permittivity of free space. The 0 reminds us that we're in free space. And it's very accurately given by this number here. The units are farads per meter. See where the units come from, like in 3318, we can derive a good old formula for the capacitance of a capacitor, and the units of capacitance are farads, and then it's obvious that that's our units, but I'm not going through that right here. But anyway, the units are farads per meter. Now, V and H, the magnetic flux density vector, units of Webers per square meter, or Tesla, is related to the magnetic field H, amps per meter, by something called mu0, the permeability of free space, the Greek mu. Again, 0 reminds us that we're in free space. I'll say a few more comments about that in just a second. Okay, but it turns out that it has an exact value. This is not an exact value. This is an exact value, and it's 4 pi times 10 to the minus 7 henries per meter. Okay, I mean, okay, if you want to be a purist, there's a footnote. mu0 had this exact value prior to a few years ago, 2019. In 2019, the physicists kind of stabbed us in the back. They got together and they decided to kind of revisit fundamental units in physics. And after 2019, a lot of things changed, including, unfortunately, the value of mu0. So it's no longer an exact value. But the good news is it's so close to this that you don't have to worry about it. So I'll just stick with calling it exactly 4 pi times 10 to the minus 7. Okay, a few more comments about that in a second. The speed of light in free space, it's approximately 3 times 10 to the 8th meters per second. But here's a more accurate value. And anyway, and we'll be deriving this before too long. It's equal to 1 over the square root of mu 0 epsilon 0. So you plug in these two numbers, you get the speed of light. Now, actually, it turns out that the speed of light is an exact number itself because it's a defined number. Now, that happened a little bit longer ago, but still not too long ago. That happened in 1983. Okay, in 1983, the physicists got together and said, enough of this business of trying to build better devices to measure the speed of light more accurately. We're getting tired of this. Let's define the speed of light to be this exact number. All right, they took the most accurate value they had at the time that they could measure, and they said, okay, from now on, this is going to be the exact speed of light. So by that, I mean, there's no more significant figures after the Z. It stops. That number right there is the exact speed of light since 1983. And you might wonder how you can get away with that. Well, it just changes things around. So after 1983, okay, it's probably still worthwhile to try to measure the speed of light more accurately. But after 1983, you're not going to change this number. After 1983, if you measure the speed of light more accurately, what you're really measuring now more accurately is what the meter is, right? Not the speed of light, because the speed of light is now a defined quantity. Okay. All right. And now, if you take this as the exact speed of light, and this is the exact mu 0, then it's easy to use this equation to solve for epsilon 0. And that's where this came from. Of course, this is not exact. That's why I put the approximate. But you can go to MATLAB and get as many significant figures as you want, right? Okay. All right. Now, a few more comments about the mu 0, because I think it's kind of a fascinating topic. I remember really prior to 2019. But anyway, I'm going to have to borrow from 3318 as I keep doing here. One of the things we do in 3318 is we look at magnetic fields from wires and then the force of a magnetic field on a wire, which is an important topic because that forms the basis, for example, how all motors work, right? Okay, but anyway, consider this experiment, if you will. 2 very long, ideally infinite wires carrying a DC current like from a battery. Wire 1, wire 2, and the distance d apart. Now, basically what happens is each wire produces a magnetic field, and that magnetic field hits the other wire and puts a force on it by something called the Lorentz force law. And that's the kind of thing we solve for in 3318, which I'm not going to do here. But here's an example of the force vector. This is the x direction. Force x component on wire 2. Now, it turns out that the two currents are equal and opposite, as shown here. Then it's a repulsive force. So force on wire 2 is down, force on wire 1 is up. They're repelling, which may be counterintuitive. If you have 2 equal and opposite charges, they attract, right? But 2 equal and opposite currents repel. That's the way it works. Okay, but anyway, the important thing I want to say is that from 3318, we derive this equation here for the force, let's say, on wire 2. Force on wire 1 is equal and opposite. So notice it's got current I squared, mu 0. That's what we're interested in, right? Mu 0, 2 pi times the distance between them. Now, this is force per meter, right? Per meter in, let's call it the z direction. Okay, so if you take a 1 meter section, then this would be really the force. Okay. Now, anyway, here is the definition. Okay, technically speaking, prior to 2019. But anyway, the official definition of what an amp is. Now, of course, you already know an amp is a coulomb per second, of course, right? But which comes first, the coulomb or the amp? Like the chicken and the egg, right? Which comes first, right? Well, the official definition of things is we define what the amp is, and once we know what an amp is and agree on that, that defines the coulomb. That's the way we really do it. Okay, so what's the definition of the amp? Here it is. Okay, the amp is the current level in these wires such that when they're 1 meter apart, the force you experience here is 2 times 10 to the minus 7 newtons per meter. That is the definition of the amp. Now, if you take that as a definition, we can't argue with it. It's just a definition, right? If we take that as a definition, the one nice thing is that allows us to solve for mu 0. Now, just rearrange this equation. Take 2 pi d over the side and divide by the I squared and plug in numbers. So 2 times 10 to the minus 7, plug in right here, right? D is 1 meter, plug in right here. 1 amp, plug in right here. It's easy to see that mu0 comes out to be exactly 4 pi times 10 to the minus 7. Right? So because of the official definition of the amp, the official, let's call it the IEEE definition of the amp, the mu0 has this exact value. Okay? That make sense? Okay. And coulomb comes from it, of course. 1 amp flowing for 1 second gives, of course, 1 coulomb, obviously. Okay. All right. Now, I mentioned in the time domain, we have these. Now, because these are just real numbers, epsilon 0, mu 0, when you convert to the phasor domain, nothing funny happens. These stay where they are, and the vector just becomes phasor vectors, right? In other words, I'm using the mathematical fact that if you have a time domain quantity that's varying sinusoidally, you multiply it by a real number. It's very simple to prove that in the phasor domain, you just take the phasor and multiply by the same real number, right? It's trivial to prove. You can do it yourself if you want. Okay. So in the phasor domain, same epsilon 0, mu 0. Okay. Okay, if we have time, why don't we work an example? Let's see if we have time here. You'll have a similar one in the homework. It's kind of interesting. It's getting us familiar with, of course, time and phasor domain, one more time, but even more important now, exercising Maxwell's equations. Okay. Now, when I plunge into this example, it may not be clear what this given electric field is. I'm not telling you what it is. I think I do at the very end of the example. If you go to the very end of the example, you'll see that it actually is the electric and magnetic fields radiated from what we call a vertical dipole antenna, a little radiating antenna element. Okay. And we'll talk about antennas in this course, but we do that at the very end. It's the last topic we do in the semester. Because if you want to see a lot more about antennas, consider taking Dr. Long's 5318 course, the antenna engineering course. Okay, but anyway, back to the example. So just assume it's a given electric field in the time domain that looks like this. Now, unit vector theta means the unit vector in spherical coordinates, which is the vector that measures going like this from the North Pole to the South Pole, is equal 0, down the negative z-axis, kind of staying like this. Okay, maybe your calculus book called it something different, but I use unit vector theta as that symbol. Okay, so anyway, we got a sinusoidally varying electric field. It's in the theta direction. Okay, it varies with a distance. It's weaker as you go out from the antenna. 1 over r has a sine theta dependence. And then the time varying part here is cosine omega t minus k0r plus some phase angle phi 0. And r simply means the distance from the origin. In other words, the usual distance in spherical coordinates. Okay, omega is the usual omega, which is 2 pi f. And k0, we'll talk a lot more later in the semester. Just think of it as a constant now. It's called the wave number of free space, and it's omega times the square mu 0 epsilon 0. When we study transmission lines and radiation, we'll see that all over the place. For now, just accept it as a constant. It's called the wave number of free space. Just a real number. Okay. All right. Now I could actually give you a frequency. I could say this is a wave radiating at 10 gigahertz or something like that. I didn't do that, so omega just left as a symbol, but it's equal to 2 pi f, of course. Now, anyway, the goal of the example is given electric field, find the magnetic field in the time domain. That's the goal. Okay. Now, I'm working it 2 different ways. Okay. First way is probably the nicest way, and that is, but you can judge yourself. The first way is I'm going to take a given field in the time domain, convert it to phasor domain, find the magnetic field in the phasor domain, and then convert back to the time domain. The second way I'll do later is I'll completely stay in the time domain and don't even go to the phasor domain. Okay, but anyway, so first thing I'm going to convert this to the phasor domain. Okay, so nothing happens to the unit vector, nothing happens to all these real terms like sine theta, 1 over r, right? So it's this cosine wave that gets converted to the phasor. Now remember, remember how cosine converts. Cosine, the general IEEE form is cosine omega t plus some phase, right? All this is really the phase. Okay, so the phasor of this cosine wave is going to be e to the j phase, so e to the j phi 0. But don't forget this is part of what we call the phase, right? Everything outside omega t. So e to the j minus k0r, e to the minus j k0r. Does everybody see that? So that's the phasor domain of this e. Now I want to find the magnetic field. So I'm going to use Maxwell's equations. Which one do I want to use? How about this one? Okay, how about this one? Okay, Faraday's law. It's got B directly in it, and I want to solve for magnetic field, so it gives it directly from the curl. All I got to do is take the curl. Since it said magnetic field instead of magnetic flux density, we interpret that as wanting to solve for H. Okay, but B is mu zero H. And then anyway, here's H in terms of the curl V. So I'll need to be taking the curl V, right? Here it is. Now, all this is spherical, so I'm going to use that formula I reviewed a little while ago, saw it in the slides, curl and spherical, there it is. Okay. Now, E only has a theta component. Strike out everything except E theta. You see it in two places here, and you see it here, right? Only two places. But this says partial of E theta with respect to phi. Now, E theta means everything in front of the unit vector. You can see it doesn't vary with phi. Now, remember, this is a fixed number. This is not angle phi, right? Okay. There's no phi variation, so that's gone too, right? So the only term that survives is this one right here. Okay. All right, there's the E one more time. And curl, again, I'm just copying down from this one right here. Okay, the recipe says multiply the theta component by R and then take the R derivative. Okay, so E theta, everything in front of the theta hat, right? All of this. The recipe says multiply by R and then take the R derivative. Now, these two R's cancel, leaving only this e to the minus jk0R. And then the R derivative of that just pulls down to minus jk0, just simple calculus. Okay, so that's the curl. And that gets substituted back into here. So don't forget the minus 1 over j omega mu 0 from Faraday's law. Okay, and then just rearrange it slightly. Okay, and you combine terms a little bit. You know, minus j cancels a minus j. You can lump k0 over omega mu 0. Okay, but anyway, it ends up giving you this. Okay, and now I'm done in the phasor domain. But what is it in the time domain? So now I go back to the phasor domain. So all this, including unit vector, all this is just real. So it just kind of tags along, doesn't really do anything. The important part is this right here. So I'm multiplying, remember, by e to the j omega t and taking the real part, right? The usual way you go back to the time domain. All this just tags along, just a real number here. Okay. So this guy right here, multiply by e to the j omega t and take the real part, which converts back to cosine, all those identities, right? So cosine omega t minus k0r plus phi0. See that? So that's the answer. So there's the magnetic field of this radiating antenna in the time domain coming from the given electric field. Okay, so we're doing the time here. Okay. Well, okay, about out of time, I guess. Okay, so I guess I better save this for next week. Okay, but anyway, the second part of the example, I'll do it one more time, but without going to the phasor domain. Okay, which had a little trick in it. Okay, so anyway, yeah, so what I suggest for next time is please read ahead, finish reading all of Maxwell's equations. And I would recommend that you go ahead and read notes 5 on the Poynting theorem if you have time to do that, because I'm pretty sure next week we'll be doing the Poynting theorem, maybe even on Tuesday. Okay. All right. Now, again, let me repeat what I said before. I don't think we have a class coming in here. So if you're free and you want to stick around and talk about homework problems or anything else, this would be a wonderful opportunity to do that. Okay. So we turn this into a problem session. So I'll stay here and feel free to stick around if you want to. Okay. And where's the sign-in fee? Okay. Thank you.
The academic honesty we can do today or next class.
I think it's at the end of the month. I mean, you can either email it to me or slip it in my door.
Okay, can I email it to you?
Sure.
Thank you.
Sure.
For the academic honesty,
Either do that or slip it under my door. Good question. What was the vector H? The official name of it is simply magnetic field.
Okay.
Yeah, and D is magnetic flux density.
Okay, thank you.
Um,
The academic